We had started this chapter 4, where we were looking into the boundary work. Our focus was to understand the boundary work and find a relationship for the boundary work. Boundary work is nothing but it is related to a closed system where one or more of the boundary of a system is moving. And the work associated with the movement of this boundary is basically described as boundary work. The relationship we developed for the boundary work is WB is equal to integral of 1 to 2 PDV. This was the boundary work that we looked into. And we said that if the process is a constant pressure process, we'll define the boundary work using this relationship where P naught represents the constant pressure and the integral of dV is basically integral of dV from 1 to 2 is basically V2 minus V1. So this is the boundary work for a constant pressure process. It's a very simple process. However, the case where we have the expansion or compression of a gas, normally the expansion and compression of a fluid within a system follows polytropic process, which is basically defined by PV to the power n equals to constant. This is a polytropic process or representation of a polytropic process in terms of pressure and volume, where n defines the path through which the expansion or compression is taking place. If the fluid within a system is following a polytropic process, we know that the boundary work could be associated with this expression, where we have seen the integration of this expression, and we know that the polytropic process follows this amount of boundary work P2 V2 minus P1 V1, and N basically represents the path through which the work done can be calculated. We further looked into another expression, and we said if the fluid within a system is following a polytropic process and the fluid within the system is an ideal gas or behaves ideally, we know when the fluid is behaving ideally, it follows PV is equals to MRT relationship. And if such a relationship exists for the fluid within a system, we can then relate the boundary work to be equivalent to MR T2 minus T1 whole over 1 minus N. This is the boundary work for a fluid which is following a polytropic process and it is behaving ideally. How did we get to this expression? We know that for an ideal process, P1 V1 is equals to MR T1 and P2 V2 is essentially equal to MR T2. So using these two expressions, we have replaced the boundary work expression with MRT2 minus T1 whole over 1 minus N. Again, the N is representing the polytropic process of different nature. Now, with these two expressions, let's say we have a fluid which is undergoing a polytropic process, or we have a fluid which is undergoing polytropic process isothermally. Uh, if we say that our fluid is ideal gas and the process is taking place, so the first assumption is that our fluid is ideal gas and the process is taking place isothermally. If these two assumptions are valid, we say that PV is equivalent to MR. Now, instead of writing T, we write T naught to represent a constant. So with these expressions, M is constant, R is constant for the gas, and T naught is constant. We can say that PV is essentially equal to C. This is valid for ideal gas that is following expansion or contraction isothermally. If we try to map this process on a isothermal process, we know that for an isothermal process, PV to the power 1 is essentially equal to constant, which is the same thing as ideal gas following an isothermal expansion or compression. Now, this means that ideal gas undergoing isothermal process is equivalent to polytropic process having N is equal to 1. I hope this is clear. With this,
Yes.
all right, with this assumption, once we integrate the um the boundary work associated with the expansion or compression of an isothermal polytropic process or an ideal gas expanding or contracting isothermally, we know that P is essentially equal to C over V, or we can say that the boundary work is essentially equal to C ln V2 over V1, where C is nothing but a constant which is represented by P1 V1 or P2 V2. For simplicity, we can write it as PV. So if you see, this is our expression. I'll erase the content. So this becomes the expression for an polytropic process where n is equal to 1, or an ideal gas expansion or compression where temperature is held constant. Now, what happens for a special case when the for the boundary work when you have a constant volume process? What do you think would be the work done, boundary work done in case of a constant volume process?
Zero.
Very good. So you know that boundary work W is integral 1 to 2 PdV. In a case where dV is equal to 0, your boundary work is essentially equal to 0. And you can visualize this by the process where it says that if the moving boundary, if your volume is constant, the moving boundary is essentially not moving. That means if the boundary is not moving, the work associated with boundary is also zero, again for a constant volume process. Now let's have a look at few of the examples to understand the process that takes place in which the boundary is moving. The first example is that of a rigid tank which contains air at 500 kilopascal and 150 degrees centigrade. So this is the condition one. As a result of heat transfer to the surroundings, it says the temperature and pressure inside the tank reduces to 65 degrees centigrade and 400 kilopascal. You have to determine the work done or the boundary work done during this process. So you have a rigid tank in which the first condition is that your pressure is 500 kilopascal and temperature is 150 degrees centigrade. As a result of some heat transfer Q out of the system, your pressure P2 becomes 400 kilopascal and your temperature T2 becomes 65 degrees centigrade. In such a case, if you have to determine the boundary work, what do you think would be the boundary work? Or how should we start determining the boundary work?
सर वो प्रीवियस जो एक्सप्रेशन है उससे भी कर सकते हैं दूसरा आइडियल गैस इक्वेशन से इनिशियल वॉल्यूम फाइंड करके और फिर ये जो दूसरी कंडीशन की में फाइनल वॉल्यूम फाइंड करके फॉर्मूले में पीवी से फाइंड कर सकते हैं
All right, one solution provided by is PV equals to MRT. So how can I find out the volume?
सर प्रेशर भी गिवन है आर भी गिवन है एम कांस्टेंट है और टेम्परेचर भी गिवन है
Pressure भी given है, R भी given है, temperature भी given है. Do you have the mass of the system?
सर मास को रहने देते हैं अब सर दो इक्वेशन बन जाएंगी दोनों फाइनल वॉल्यूम और इनिशियल वॉल्यूम का रेशो ले लेंगे
All right, मैं ऐसे लिख लेता हूँ P1 V1 over T1 is equals to P2 V2 over T2. ऐसे कर सकते हैं? जी, V1 और V2, do you have these values?
सर पिछली स्लाइड शो करना इसकी भी सर जो पीवी है उनकी इंटीग्रेशन जो अगर हम दोनों चेंज हो रहे हैं तो इंटीग्रेशन बाय पार्ट्स कर ले वो हो सकता है दोनों चेंज हो रहे हैं दोनों की इंटीग्रेशन करेंगे
आप बताएं ना कैसे करेंगे. Go back to the statement Have a look at the statement very carefully.
सर वॉल्यूम दोनों की कॉन्स्ट सेम है रिजिड टैंक
Yes, the critical word over here is the rigid tank. This is the most critical word of the statement. This means that a rigid tank means that V1 is essentially equal to V2 is essentially equal to zero. Oh, sorry, is essentially equal to constant. So that means dV is essentially equal to zero. In a case where dV is equal to zero, what is the boundary work?
zero.
So boundary work 1 to 2 PdV, where dV is equal to 0, is essentially 0. Alright, so your boundary work in this case would be 0. And if you have to plot this process, the easiest thing is you plot the process on a PV diagram. Your first state says that your pressure is 500 kilopascal and your volume is some, assume any volume. This is your state 1. At a second state, your pressure is 400 kilopascal and your volume is the same. So if you see from 1 to 2, the area under the curve is what? Area under the curve is 0.
Zero.
That means your work done is essentially 0 for the boundary work done is essentially 0 for this process. Clear enough?
Yes, sir.
All right. So same thing, your PdV, dV is 0, your work done would be 0, 1 to 2, the area under the curve is 0, so your work done would essentially be equal to 0. Now moving on, you have another example which says that a piston cylinder device initially contains zero point 0.4 meter cube of air at 100 kilopascal and 80 degrees centigrade. The air is now compressed to 0.1 meter cube in such a way that the temperature inside the cylinder remains constant. You have to determine the work done during this process, or the boundary work done during this process. So how would you determine the work done?
सर प्रोसेस आइसोथर्म में है तो n इक्वल टू 1 है और वो फार्मूला यूज करेंगे c इक्वल c ln of v2 divided by v1.
All right. But before that, there are two things or two assumptions you have to make. Number one is that your process is a quasi-equilibrium process or quasi-static process, that compression is taking place slowly. So at all times, your system is at equilibrium. The second assumption is that you will assume that air is behaving ideally or as an ideal gas, which is a fair assumption. Once you have these two assumptions with you, you can apply the equation which is PV equals to MR T naught, or PV equals to constant, in which the boundary work is essentially equal to C ln V2 over V1. This is the expression in which C is a constant, and you can say that C is P1 V1 ln V2 over V1 in order to calculate the boundary work. Why can't I use P2 V2 ln V2 over V1? It would be difficult for me to use P2V2 since the final pressure is not given to me. Although I can find it out using the ideal gas equation, but I'll stick to P1 V1 ln V2 over V1. So this is the uh, process path where your system is basically moving from 1 to 2 isothermally on a PV diagram. And if you do the integration, you'll have ln v2 c ln v2 over v1, or p1 v1 ln v2 over v1 as the integration. Once you plug in the values, what do you expect the boundary work to be, positive or negative?
सर नेगेटिव होना चाहिए नेगेटिव होगा वर्क डन ऑन द सिस्टम है
Yes, very good. So whenever your compression is taking place, your boundary work would be negative, and whenever your expansion is taking place, your boundary work would be positive. So once you solve it out, you'll come to know that your boundary work is essentially minus 55 kilojoule, 55.5 kilojoules, which is associated with the compression process. All right. Now let's move on to a little more uh, difficult example. It's a relatively difficult example. Let's have a look at the statement first. It says that your gas, you have a cylinder device piston cylinder device which contains 0.05 meter cube of a gas initially at 200 kilopascal. At this state, a linear spring that has a spring constant of 150 kilonewton per meter is touching the piston but exerting no force on it. Then he says that now heat is transferred to the gas, causing the piston to rise and to compress the spring until the volume inside the cylinder doubles. If the cross-sectional area is 0.25 meters square, determine the final pressure inside the cylinder, the total work done by the gas, and the fraction of this work done against the spring to compress it. Now let's have a look and understand that this is your state 1. In this state 1, this is your piston, and there is a spring which is being attached to the body, and it is just touching the piston head. It is not exerting any force, and the pressure inside is 200 kilopascal. This is your state 1. Now tell me, if the pressure inside the cylinder is 200 kilopascal, what is the pressure inside the cylinder balancing actually?
सर 200 किलो पास्कल ही पिस्टन का वेट अगर उसको कंसीडर ना करें.
All right. So yes, very good. So essentially, it is balancing 200 kilopascal, which is due to the atmospheric pressure plus the pressure due to the weight of the piston. So together, the weight acting on this system is 200 kilopascal, and the pressure inside is balancing this external pressure due to atmospheric pressure and the weight of the piston. Is this point clear to you?
Yes sir.
All right. Now it says that some heat is being added to the system and your system moves to condition 2 where the piston has moved upwards, and as a result of this upward movement, the spring that was attached is essentially compressed. All right. So this is your state 2. Now I know that uh, has the atmospheric pressure or the weight of piston changed?
No sir.
So that means essentially the pressure at final state P2 is 200 kilopascal, which it is acting against, which is it is showing against the atmospheric pressure in the piston plus some other pressure. Is this clear? There are two pressures acting on
Yes
the
sir.
system now, external pressures. One pressure is due to the atmospheric pressure and the weight of the piston, which is essentially 200 kilopascal. What is the second pressure?
Sir, due to the compression of spring.
So the second pressure is due to the compression of spring, which is I have written as C spring or compression of spring. So the final pressure, if you have to calculate, it is 200 plus the pressure caused by the spring. Clear up till this point?
Yes sir.
All right. Now, if I have to determine the pressure due to spring, let's first find out the distance which the spring has moved or spring has compressed. If I say that my volume has doubled, so what is essentially the change in volume?
0.05 meter cube.
Very good. So 0.05 meter cube is the change in the volume. And if I know, I already know that volume is essentially what? Volume is area into the length.
Yes sir.
And the cross-sectional area is 0.25 meter square, which is constant. So if I have 0.05 as a change in volume, which is essentially equal to area into length, my area is 0.25. L basically represents what? L represents the distance x which is being moved by the spring. Clear
Yes
now?
sir.
Now, if I know the distance x which has been moved by the spring, can I determine the force which the spring is acting on the piston head?
Yes sir.
Yes, so if it is equal to, it's a linear spring, it is equal to F is equal to Kx. All right.
Yes sir.
Now, F,
सर
sorry.
सर अभी हमने ये जो फॉर्मूला अप्लाई किया है यहाँ पे हम वॉल्यूम की जो बात कर रहे हैं वो भी हमारे यानी हमारे सिस्टम का है जो कि पिस्टन के नीचे है और जो एरिया वो भी पिस्टन का है तो फिर हम लेंथ को कैसे कह सकते हैं कि ये स्प्रिंग ने मूव की है ये तो ये कह सकते हैं हम पिस्टन ने मूव किया है
अच्छा, ये अगर पिस्टन इस वक्त यहाँ पे है, ऑलराइट, और फिर
जी
पिस्टन यहाँ पे आ जाता है, ठीक है।
जी जी
अच्छा, दिस आई से एज, हाँ, वेयर इज इट, दिस इज माय स्टेट 1, दिस इज माय स्टेट 2। नाउ इफ आई हैव, ये मेरी पहली कंडीशन है, यहाँ पे मेरा स्प्रिंग लगा हुआ है इस जगह पे, ऑलराइट। इज दिस क्लियर, द स्टेट 1।
जी सर।
और जब ये ऊपर की तरफ मूव होता है तो मेरा स्प्रिंग जो है वो इसेंशियली यहाँ पे आ गया, क्लियर।
जी
सो इसेंशियली जितना डिस्टेंस पिस्टन ऊपर मूव किया है उतना ही स्प्रिंग ऊपर की तरफ कंप्रेस हुआ है,
ऐसा ही है।
क्लियर इनफ।
जी जी
So if I can find out the length x which the piston has moved, it would be the same as the movement of the spring.
जी ठीक।
All right. So if I know the length of the movement of the piston, it is essentially equal to the distance moved by the spring, which is x. If I know that, I can apply the Hooke's law and say that F is equals to kx. K is known to me since it says that it's a linear spring. So you can apply the Hooke's law, which says F is equals to kx. K is essentially what? 150 kilonewton per meter. X is known to you. You can find out the force associated with the spring. Is it clear to you? Clear enough?
यस सर।
Now, if I divide the force of spring by the cross-sectional area, this would be equal to what? Pressure due to spring.
Yes, sir.
So essentially, I can find out the pressure due to spring alone.
Yes, sir.
Yes,
All
sir.
right. Now let's move on and see the solution first. So this is the volume, which has essentially doubled, 0.1 meter cube. If the volume has doubled, your x, or the displacement of piston, which is basically that of the spring also, would essentially be the change in volume, which is 0.05 divided by the cross-sectional area, which is 0.2 meters. If I know the length for which the piston or the spring has moved, I can essentially multiply the spring constant with the length through which the spring has moved to find out the force that is acting on the piston head due to the linear spring. And if I know the force, I can divide it by the cross-sectional area to find out the pressure acting on the system due to the spring. So if I know the pressure acting due to this movement of the spring, what is the total pressure acting, or what is the total pressure inside the cylinder then?
Initial pressure plus pressure due to spring.
So the initial pressure is 200 kilopascal. This is balancing the atmospheric pressure plus the weight of the piston, and this is basically due to the spring. So the total pressure comes out to be 320 kilopascal. Now I have to determine the total work done during this process. How can I find out the total work done?
सर P1 P2 है, V1 और V2 भी है। इक्वेशन हमारे पास है पहले स्लाइड में।
कहाँ पे है P1 V1 और P2 V2?
सर P1
ऑलराइट,
हमारे पास 200 किलो पास्कल है और P2 हमने भी निकाला है 320।
ठीक है,
और वॉल्यूम इनिशियल जो था वो 0.05 था, बाद में 0.1।
ठीक है। तो हम क्या करें फिर?
सर इसकी इक्वेशन थी ना पिछली स्लाइड पे।
इक्वेशन थी? कौन सी स्लाइड पे इसकी इक्वेशन है?
सर पिछली स्लाइड करना।
ये ले,
सर इससे पिछली।
ये ले।
सर लेकिन इसमें P कांस्टेंट था। इस दोनों को अब जो प्रॉब्लम है उसमें
सर
P
ये
P
जो WP
चेंज हो।
इज इक्वल टू P2 V2 माइनस P1 V1 और 1 माइनस n।
चैन क्या है? Let's go back and have a look at the example.
सर मगर ये तो बाउंड्री वर्क नहीं, हमने तो वो निकालना जो कि सिस्टम ने किया है।
Yes, the total work बाउंड्री वर्क है ना, पिस्टन की मूवमेंट है ना। पिस्टन की मूवमेंट एक्सटर्नल प्रेशर पर डिपेंडेंट है. Let's first, अच्छा, we'll try to solve it using a simpler approach. Simpler approach क्या है? That we have this system with us and let's try to
एरिया
give
अंडर.
this. जी जी बिल्कुल, very good. So you have this first condition where your pressure is 200 kilopascal and your volume is 0.05. Then you have the final volume to be 0.01 and your final pressure is essentially 320 kilopascal. So this is your state 2, this is your state 1, and your process path is basically this line. This line basically represents your process path. So if you need to find out the total work done, it would be essentially the total area under the curve. Clear enough?
यस सर.
All right. So you can, if you see, this is essentially what, if I uh, highlight the bound.
Trapezium.
G, very good. It's a trapezium. So let me highlight the boundary so that it becomes easier for the rest of you to understand. This is essentially two parallel sides, and this is the perpendicular distance between two parallel sides. This is essentially a trapezium. If you see the length from here to here, this length is essentially what? This is essentially 320.
यस सर.
This length is 200, again kilopascal, and the perpendicular length is 0.05. So the area for the trapezium, which is area for the trapezium is half into sum of parallel sides multiplied by uh, the distance between the perpendicular distance between the parallel sides. So it would be what? Half into 200 plus 320 kilopascal multiplied by 0.05. This would give you the total area under the curve. Clear enough?
यस सर.
All right. Now I'll erase the ink. Now you see these are the two. This is the schematic of pressure specific volume pressure volume diagram for the process path, and if you calculate the area under the curve, which is sum of parallel sides multiplied by the perpendicular distance between the parallel sides divided by 2 would give you the total work done in kilojoules. Why kilojoules? Because you're using kilopascal. Clear enough?
Yes, sir.
All right. Now, how would you find out the area or the work done by the piston against the spring or the spring work done?
1/2 kx square.
1 by 2 kx square. In this, you have to be very careful in which you have to use x1 and x2 because you know that this distance has moved from some x value to another x value. That is the correct way. You can do it using the spring equation. But there is another equation or there is another way to find out if you want to integrate differentiate between this one area 1 and area 2, the two different colors. These are two different work done or work done against two different external forces. One is the work done where your external pressure or external resistance is 200 kilopascal. That means this 200 kilopascal moved for this much distance gave you work done 1. So this area, it is the work done against which resistance?
Atmospheric pressure,
Atmospheric
weight of
pressure.
piston only.
Very good. So it is against atmospheric pressure and the weight of the piston. And this work done too is against
Against
what?
spring.
So this is the work done against the spring. So if I simply calculate the area of this triangle, which is half base into height, this length would be essentially 320 minus 200. This length you already know is 0.05. So half base into height would give you the essential area. You can always use the kx square equation also. So half base into height would give you the work done against the spring. Clear?
Excuse me, sir.
जी.
Yes sir.
बेसिकली इधर हमने जो बाउंड्री वर्क फाइंड किए तो वो ग्राफिकली फाइंड किया. अगर हमने न्यूमेरिकली फाइंड करना होगा तो कौन सी इक्वेशन यूज करेंगे?
न्यूमेरिकली फाइंड आउट करना है तो यू हैव पॉइंट वन जिसमें P1 की वैल्यू भी है और V1 की वैल्यू भी है. यू हैव पॉइंट टू जिसमें P2 की वैल्यू भी है, V2 की वैल्यू भी है. डेवलप अ लीनियर equation between P and V. So you will have a linear equation between P and V जो कि इस line को represent करेगी, which is of the sort of y is equals to mx plus c. ये आपके पास इस sort की एक equation आएगी P और V की, which would be then placed in the integral P dV. When you'll have an equation in the form of P and V, you'll replace P and have an equation in terms of V and a constant. And then once you integrate, you will find out the boundary work done. Clear enough?
Yes, sir. Thank you.
All right, you're welcome. All right, energy balance for a closed system. Energy balance for a closed system, again, you know it is E in minus E out, change in energy of the system. This is what is coming into the system and out, going out of the system in terms of heat, work, and mass. And the change in energy of the system is represented by change in internal kinetic and potential energy. You already know this equation. Similarly, in the rate form, you'll have a dot on top of it. You already know this. And the total quantities are related per unit time. If you have the heat transfer rate given to you, you multiply it by the time for which that took place, and you can find out the total heat transfer. Similarly, the work done, the rate of work done is given to you, you multiply it by the time for which it has been done, you'll find out the total work done. And similarly, the total change in energy of the system is the rate of change of energy of the system multiplied by the time for which that took place. So these equations are known to you. Essentially, what I want to highlight over here is that E in basically E in minus E out. For a closed system, E in is basically Q in plus W in, and E out is Q out minus W out. This is essentially equal to change in energy of the system. It's the same equation. I have split it into heat and work. And I can sometime combine these two, Q in minus Q out, as Q in minus Q out, and I can write them as either Q, or I can write them as Q net into the system. These two terminologies are normally used when I combine Q in minus Q out. Q in minus Q out can sometimes be written as Q, or can also be written as Q net in. Similarly, work in and work out, they are combined together as work out minus work in, and you have a negative sign outwards. So it could be written as work or work net out. So you can have, at times you can see an equation where it is written Q minus W equals to change in energy of the system, or Q net in minus work net out is equals to change in energy of the system. These two equations, this equation and this equation, they are all the same equation. It's just the way how you express the equation. Clear?
Yes, sir.
This is per unit mass. So if you have expressed in terms of Q or Q net in, or you have expressed in terms of W or W net out, remember that heat input and work output, heat input and work output, they are considered to be as positive, and heat output, which is Q out, and work input, they are considered to be as negative in these equations. I've already explained this to you, that Q net in minus W net out, or Q minus W in, is equals to change of the system. Sometimes the equation is expressed in this form. Again, for a cyclic process, you know that change in energy of the system is essentially equal to 0. In such a case, you would essentially have Q equals to W, or Q net into the system is essentially equal to work net out of the system. So that means if you start from this point 1, you move along a closed loop and come back to the same position, your change in energy of the system is 0, and Q is essentially equal to W. So the heat transfer coming to the system is work going out of the system. And some of the expressions that would be used commonly in closed system is Q minus W is equals to delta E. Again, Q net in, W net out is referred by Q and W. Stationary systems, you will have delta U instead of delta E. Per unit mass, you will have small letters, and differential form, you will have inexact differentials for these two, which are path dependent functions, and exact differential for dE, which is a state dependent function. Now, the last thing for today's slide is energy balance for a constant pressure expansion or compression process. You know the equation Q minus W is change in energy of the system. I'll split this W into two forms. One is the boundary work. So this is the work in which boundary of a closed system is moving. And W other refers to all other forms of work, whether it is electric heater fitted into the system, moving shaft in the system, all the works in which moving boundary is not involved, you refer to it as W other, and the work which involves the movement of the boundary is referred to as WB. So if you have the closed system, your equation would essentially be closed stationary system. Your equation would essentially be Q minus W is equal to delta U, since kinetic and potential energies are essentially zero. Clear enough so far?
Yes, sir.
All right. Now I split W into two other forms, which is WB and W other. So I have splitted this into W other, which includes all work except for boundary work and the boundary work itself. And if you know that boundary work is what? Integral 1 to 2 PdV. And for a constant pressure process, this would be equal to P naught V2 minus V1. So for a constant pressure process, I can represent boundary work as minus P naught V2 minus V1. Clear enough?
Yes, sir.
And if I take the boundary work on the other side, I would essentially have Q minus work other is U2 plus P2 V2 or minus U1 plus P1 V1. And essentially P naught is equal to P1 is equals to P2. So whether I write P naught over here or P1 or P2, it's the same thing. So I prefer writing P1 over here and P2 over here. Clear enough? And by default, you know the combination property, which is enthalpy, is nothing but the combination of internal energy plus the flow work, which is PV. So H is equals to internal energy plus PV is a combination property which we have already discussed and defined. So if H is equals to U plus PV, we can express this equation in the form for a constant pressure process, Q minus work other is essentially equal to change in enthalpy of the system. Clear enough? So what I'll do is that I'll stop over here and we'll begin with the same point next in the next class, which is